Hi, my name is Shai Shalev-Shwartz from Mobileye, and I will talk about the challenges of building safe autonomous vehicles. Self-driving systems are unique in the sense that we need to build a very sophisticated technology, um, and at the same time, it must have an extremely high accuracy. So we have technologies that are very sophisticated, like the smartphone that we are holding in our hand, but it has low accuracy requirements. On the other hand, we have simple technologies like airplanes that achieves an extremely high accuracy requirements. But in autonomous vehicle, we need both a very sophisticated technology and at the same time one that requires extremely high accuracy. How accurate? So just a back of the envelope calculation. Humans in accident that involves injury for human drivers happen approximately every 10,000 hours, and accidents that involve fatalities happens approximately every 1 million hours. So we need to aim for a bit more than that. So it means that the mean time between failures, MTBF for short, must be at least 10 to the power of 7, meaning 10 million hours, and probably more. How can we achieve this level of accuracy? How can we validate the accuracy of the AV system? So, in order to tackle the problem of building a sophisticated technology with extremely high accuracy, we look at the sense, plan, and act methodology from robotics. Um, Sensing is a perception of the environment. We need to build a world model of the vehicle surrounding, understanding where we are, what are the other road users around us, obstacles around us, traffic lights, etc. Planning is the decision making part, and acting is the execution of the plan. So in the planning, we decide how to drive, and acting is actually steering and braking and accelerating in order to implement the plan. Most of the talk I will devote to the sensing problem, but at the end I will also briefly mention the planning part. Okay, so how can we tackle the perception problem, the sensing problem? Our approach is based on the simple concept of redundancy. Basically, we aim at building two fully independent subsystems. One is based on cameras alone, the other one is based on radars and lidars alone. Each one of them should reach a mean time between failure of 10,000 hours at least. And then, if we take the worst case among the two, we can achieve a very high safety standard. If the two systems are truly independent, then the MTBF of the combined system is roughly the product of the MTBF of the two individual systems. So now the challenge is to build a fully independent camera-based sensing system that can reach 10,000 hours MTBF. Okay, so what are the challenges of building a camera-based perception? The first challenge is that cameras are inherently a 2D sensor and we need a 3D understanding of the world. The second challenge is that we need an extremely high accuracy even in edge cases. So to understand the first issue, here is a video of a car in a flood. This was, you weren't supposed to see this, but let's see. So we see the car, it seems like a car in a flood, but then we see that it's a toy car of a little kid that play with it. So we see that cameras are really 2D sensors. There is no way to know from the beginning of the video that this is a toy car which is not and not a real car. All right. So continuing. If you want to understand this issue, in the image plane, two people, one is short and one is tall, but they are at different distances from the camera, will look exactly the same on the camera. Beside that, cameras depend on lighting conditions, so we need to be robust to very difficult lighting conditions. Rain situations, foggy situations, and in addition, there are many corner cases. Like here, we see a tree that is moving on the road. It's actually attached to some truck, or a house that is moving on the road, and it is actually uh, on a truck. On the other hand, we see here a truck, and there is a house and a tree on the truck, but they are not attached to the truck, and they are not part of the truck. So things can be tricky. Also, very strange looking trucks and stuff like that. Okay. How can we tackle these difficulties? Starting from lifting 2D to 3D. Basically, I will describe three approaches to lift 2D to 3D. The first one is if we know the object dimension, then we can convert its image location into its 3D location. We can lift from 2D to 3D by knowing the dimensions of an object. So we can try to predict the dimensions of the object. It will not always work, like we saw in the video of the toy car, but in most of the cases it will work. Other two methods are based on stereo technology or structure from motion technology, equipped with deep networks. And the third approach is not even working on the 3D world, but working on a different world, and I will elaborate later. So for the first approach, if you know the height of an object, we can know also its position, very simple. The second approach is stereo technology, but it's not a naive stereo technology which does not have enough range and robustness to the scene. Instead, we combine deep learning and stereo technology. We call it a VIDAR, which is a visual LiDAR. So this video here shows you the output of a VIDAR system. Based on few cameras, it predicts the depth of every pixel. So you can see that we pretty much get a depth image based on cameras which are inherently a 2D sensor. Another example, this is a network that we call parallax network. The idea here is structure from motion combined with deep learning. We predict for every pixel in the image its elevation from the road surface. Okay, the third approach is not even using 3D information, but instead taking the 3D world and projecting it into 2D world and then working the 2D world. How to do this? Suppose that we know our location on a map, then we can project the map. The map is in the 3D world and we can project it onto the 2D world. And this is easy from 3D to 2D. The difficult direction is from 2D to 3D. And then we can work in the map coordinate system. So we can locate, for example, this car, we can locate it on the map instead of on the 3D world. And then from this we can continue our system. So what you see here is a projection of a map on the image plane, which allows you to know the location of objects on the map. Right, so this was about lifting 2D to 3D. The second challenge is with that we need extremely high accuracy, even 10 to the fourth 10,000 hours. One failure in 10,000 hours is an extremely high accuracy. And we need to be able to tackle edge cases. The way we tackle it is, again, by using many redundant systems. So we built many different technologies to predict the same thing. For example, if we need to detect vehicles, we will both try to detect the vehicles, but we will also try to detect wheels. We also try to detect for every pixel in the image its semantic meaning. To put boxes on cars, to predict the full image, to predict the top view, and this is both for detection and measurement. So just to see some examples, so here is a wheels detection system. You can see that in many situations here, to put a box on this entire truck with trailer may be tricky, but we can see the wheels very nicely. So from the wheels we can know exactly what to do. So this is one example. Similarly, scene segmentation. So here we see for every pixel we detect its semantic meaning. Now watch carefully what happens. Whoops. I will do it in slow motion. This truck with trailer on the left, something flies out of the truck, and as you can see, we detect it perfectly and understand that even though it doesn't look like something that should be or should fly on the road, we understand that it's not a road, and then we can be careful about it. So there are many more systems that try to do semantic segmentation, pixel level segmentation, etc., etc. Okay. So, to sum up the part on sensing, there are two main challenges, going from 2D to 3D and extremely high accuracy, and I described some methods to do this. The next part is about the decision making, the driving policy. So again, typically we first need to sense, to understand what's around us. Then we need to decide what to do, to plan, and then we need to act. I'm going to talk about safety of the second component, the planning. So what does it mean, safety of the planning part? So we can try to say, let's avoid accidents at all costs. But then we see that it doesn't really make sense. So consider this scenario. This is a typical highway situation. We are the yellow car. There are red cars around us that are driven by human drivers. Then suddenly one of the drivers swerve into us. There is nothing we can do. We have nowhere to run away and avoid the accident. So avoiding these accidents at all cost, meaning that we are not allowed to be in this situation, but this means that we cannot drive on the highway. So this is a major issue, which we call the usefulness safety trade-off. We must be agile. We must blend with other cars. And it's actually an ethical question. How fast should we drive in a residential road? The current law is not sufficient for avoiding all accidents. If you drive at a loud speed, according to the traffic sign, as most people do, then you are likely to cause death in case a little kid will run into the road. So the allowed speed is set so as to facilitate some balance between safety and reasonable flow of traffic. Um, and in general, this question of balancing the usefulness and safety trade-off is an ethical question. The law just requires to be cautious. But what does it mean? How can we require machines to be cautious? So if we look at the law, there is a law that's called duty of care. It's a legal obligation which is imposed on an individual requiring adherence to standard of reasonable care while performing any act that could foreseeably harm others. So humans seem to possess some common sense as how to interpret this law. Can we design machine who possess this common sense? What we do is we propose a rigorous mathematical interpretation of this law, which is applicable to self-driving cars. I will not elaborate too much on this model, but the properties of this model is that it is sound, it complies with the common sense of human driving, and it even guarantees zero accidents in an utopic world where all the road agents adhere to the interpretation of the duty of care. It is useful. It allows scaling to millions of cars without blocking the traffic, and it is applicable to machines. It is by design ensure that a self-driving car always obeys the law, and this is far from being trivial because of potentially butterfly effect. So our proposal, RSS, stands for Responsibility Sensitive Safety, is a mathematical model formalizing a common sense interpretation of the duty of care. It formalizes what is a dangerous situation, what is a proper response to a dangerous situation, and what does it mean to be reasonably cautious. To sum up, autonomous vehicles pose a very challenging task because we need to build a very sophisticated technology that requires an extremely high accuracy. Our two main components for tackling the challenges are first, for sensing, redundancy. We built every system in many different ways in order that at least one of them will work. And for the planning part, we designed a formal model of safety which guarantees that we will not have lapse of judgment. So thank you very much for watching.